Okay, so now we have the whole point of this chapter is to prove this theorem. So we're going to pull together everything we've done so far. What does the theorem say? Suppose we have a finite group of automorphisms of a field K. Okay, so G is going to be our finite group, and it's a subgroup of the automorphism group of K. It's just a finite group of automorphisms. That's all it is. And we're going to set K0 to be the fixed field. So K0 is the field that's fixed by every element of the group. Then what? Then the degree of the extension that we get, because K0 is going to be a subfield of K, right? It's the guys in K that are fixed by G. We showed that was a subfield. The degree of that corresponding extension is the number of elements of the group. Okay. All right, this is going to be a long proof, so I apologize in advance, but it's kind of unavoidable. So suppose n is the order of the group, and we label G1 through Gn and G just the elements, the distinct elements. Now keep in mind these are automorphisms. And automorphisms are isomorphisms from the field to itself. In particular, they are special monomorphisms. So the Dedekind lemma is going to apply here. And we are going to set, one of these has to be the identity element of the group. We're going to make sure that G1 is the identity. So we are going to prove that the degree of K0 bigger than n, and K at K0, degree of K over K0 less than n are not possible. And that's going to mean then that the degree of K over the fixed field is exactly n. So we're going to do these cases separately. For the first case, we're going to suppose the degree of K over K0 is m, which is less than n. Okay, so we have the degree of our extension is less than the order of the group. We are going to let x1 through xm be a basis for K over K0. All right. Now, what can we do? Well, for each xi, G1 of xi all the way up to Gn of xi are linearly dependent. Why is that? Well, the g's may do different things to the xi's, but there's more. How many outputs are there? There's n outputs, and the size of a basis is m. So there's more vectors than in a basis, so they're linearly dependent. All right, so that is then, there exists, how do I want to say this? Let me say it like this. We can consider the system y1 g1 of xi all the way up to yn gn of xi is 0. So let me just say what's going on here. So like in the lemma that we talked about, here the ai1s all the way up to the ain's, these are our g1 of xi's, and the x's, those are the y's. Okay, so the coefficients here of the y's are these guys here. So what do we get here? We get a system, right, as I runs over the basis elements. And in this system, we have more unknowns than we have equations. So it's underdetermined. So not only are they linearly dependent for each I, there's a non-zero solution that works for all of them. Solution y1 through yn in K. All right, and now it's going to get a little bit complicated. We're going to evaluate the y's, sorry, the gi's on a general element of k naught. That is, we're going to evaluate this combination on a general element. So remember, we have a non-zero solution to this system of equations where we've plugged in a basis. And basically what this is saying is we're zero, this combination, this non-zero combination is zero on a basis. If you're zero on a basis, you're zero on everything. So that's what we're going to show next. It's going to be a little tedious. So we're going to set we're going to pick any x and k. Then what? There exists a alpha 1 through alpha m in k naught such that x is alpha 1 x1 plus alpha m xm. Then what? Well, then let's look at this combination of the g's evaluated at x. Okay, so let's use some shorthand. I'm going to say this is the sum on L alpha L XL. So we can get y1 g1 of this sum. And the g's, of course, are linear, so we can bring that sum out. Oops, I don't know what happened there. So we have the sum on alpha L y1 of g1 of XL all the way up to the sum on alpha L yn gn of XL. And then, of course, we can bring this together under one sum because they're all summed over the L index. But this is, we've plugged in the basis into the g's now, and we know that the y's make it so that this combination is 0. So what are we adding up? We're adding up the sum on alpha L times 0, which is, of course, the sum of 0, which is, of course, 0. So what did we learn here? We learned that the g1 through gn are linearly independent, which is a contradiction. Or linearly dependent, rather, which is a contradiction. Because Dedekind's lemma says they are independent. Okay? So we've achieved a contradiction in what case? When the case in the case the degree of k over k naught is less than n. All right. So now for the second case, we're going to suppose the degree of k over k naught is m, but that's bigger than n. So what does that mean? Since it's bigger than n, there exists, well, at least n plus 1 linearly independent elements of k over k naught. Right? It says the size of a basis is at least n plus 1 if the degree is bigger than n. We don't need all of them, everything in the basis. We just need n plus 1 of them. Let's say that these elements are x1 through xn plus 1. All right. Now what? Now we're going to create a similar system. We're going to consider the system y1 gj of x1 all the way up to yn plus 1 gj of xn plus 1 equals 0 for j in between 1 and n this time. So how is that different from the system we just looked at? Well, here we get an equation for each element of g. Before, we got an equation for each basis vector. So we're switching which index we vary. Right? We switch the index that we varied. And so what do we have here? Well, we have the system here. It's a system of n equations, in n plus 1 unknowns, right? Because these guys are just constants. They're elements of k, so we have n plus 1 unknowns, and we have n equations. So it's a underdetermined system, so there exists a non-zero solution. y1 all the way up to yn plus 1 in k. So we have some non-zero combination of the g's such that when we do this, sorry, of the gj of xi's, such that when we do this, we do the corresponding linear combination, we get 0. All right. So now what? Well, we're going to choose maybe after renumbering. Well, let me say it like this. After maybe relabeling, we're going to suppose that the first r are not 0, and then the last ones are 0. Now it could be that r is n plus 1. It could be that they're all non-zero, but we're gonna organize them so that maybe after renumbering them, the first however many non-zero ones show up, and after that, that's when the zero coefficients could show up. Because a non-zero solution might have some of them being zero, so we just put the non-zero ones in the front. Okay, so since all of these other guys are 0, our system is going to become, or our equation becomes, I'm going to write system. What does it become? It becomes y1 gj x1, and now we only go up to yr gj xr. All right, now what? Well, for each g and g, we can apply it. And when we apply g, on the left-hand side, g is a monomorphism, so it breaks up under multiplication. And this is the composite of the g's. So this, we get g of y1, and then we get sort of g times gj x1, g of yr, and then sort of g times gj of xr. All right, great. But left multiplication by g, remember how many equations do we have here? We have n equations, one for each element of g. Left multiplication by g is a bijection. And so as j runs over all the elements of g, g times gj also runs over all the elements of g. So the system that we have here, these equations, are the same as just running over with a single element. And I'm just going to relabel that as a j to not confuse indices. It doesn't matter what we use as a dummy variable. It's just a dummy variable. All right. Now what? Well, we sort of have two systems. We have this one, and then we have this one. And so what we're going to do is on this guy, we're going to multiply by g of y1. And on this one, we're going to multiply by y1. And then when we do that, we're going to subtract them. So what's going to happen when we subtract this system from the other system when we multiply every element of the equation by g of y1 and every element in this system of equations by y1. Well, the first terms are going to cancel, and we're just going to be left with what happens in the last bit, right? Because the first terms are exactly the same term. So multiplying original system. Sorry, I know this video is getting long. We're almost done. Original system by g of y1 and new by y1, then subtracting yields what? Well, we're only going to get the y2 terms and higher. So we're going to get y2 g of y1 minus g of y2 y1 gj of x2 all the way up to yr g of y1, oops, minus g of yr y1 gr of xr. So what did we get here? Well, we chose our y's. We chose this r so that all of the non-zero coefficients were in the beginning, and we want to choose the non-zero solution. I forgot to put this here. Non-zero solution with the minimum number of non-zero terms. So you cannot get any less non-zero terms. And what did we find? Well, we found that actually you can get one less, right? We no longer have we no longer have the gj of x1. We've gotten rid of one of them. Okay. So we will have a contradiction unless all the coefficients happen to be 0. So so we conclude then that yi g of y1 minus y1 g of yi is 0. And this tells us then yi g of y1 minus equals y1 g of yi, or equivalently by multiplying by a y1 inverse yi is g of yi g of y1 inverse, which is the same thing as saying y1 inverse yi is, I guess we're in a field so it doesn't matter what the order is that. And this should be true for all g and g. So what does it mean that it's true for all g and g? Well, it means that g fixes these elements y1 inverse yi. So these guys are in the fixed field for all 1 less than or equal to I less than or equal to R. All right. Now what? Okay. Oh, sorry, I made a mistake here. Now what? Well, what do we have here? Well, they're in the fixed field, so there exists zi in the fixed field, k0, such that y1 inverse yi is equal to zi, or yi is some fixed element times zi. So this y1 is fixed for all I. Okay, so this guy here is the same y for all I. All right, now what? We're almost there. We're going to look at one of these equations. We're going to look at this first one here, and we are going to look at this when j is equal to 1. When j is equal to 1, g1 was the identity. So what does this say when j is equal to 1? It says x1 y1 plus x2 y2 plus x r yr is 0. So we know a priori that x1 y1 plus x2 y2 all the way up to xr yr is 0 by plugging in j equals 1 in that equation. And now we have a formula here. We have x1 y1 z1. This is even true for I equals 1. This is a little bit weird. It should just be a y1 here. plus x2 y1 z2. I want to put the z1 for emphasis, although it's z1 is technically 1 in that case. I'm going to put it for emphasis, sorry. z1 plus x2 y2 z2 all the way up to xr y y1 zr is 0. Now we have a common, oh shoot, that should be a y1. We have a common y1 everywhere, so we're going to divide by that y1. And what do we have here? Well, the z's are not 0. Because the y's weren't 0. And so we have a linear combination of some elements of our linearly independent set being 0. That's a contradiction. So this is a linear dependence among linearly independent elements, which is a contradiction. Great. All right. So we've reached a contradiction in the bigger than n case and the less than n case. Thus, what can we conclude? Well, the degree of k over k naught must be exactly n, because we get a contradiction otherwise. So this proof was really long, sorry, but it's kind of unavoidable.